Okay, let's talk propulsion force during cycling. All right, so I've drawn a bad picture of a bike. That's the best I can do. And I have identified the propulsion force. Now, we've already done a kinetic analysis of cycling, and we've identified all the forces acting on the bike rider system. I conveniently left the biker out of the picture here because I do a terrible job of drawing that stick figure on the bike. Nevertheless, this is the bike, and there's a rider on here, and that rider is pushing right here. I'm going to say F of the person is pushing on the pedal, and that's going to make the pedal spin around. And remember, we have the big chain ring right here. And then we've got the little chain ring right here, the cog right here, the rear cassette. And we have a chain connecting those two. The person pushes on the pedal to turn the crank. That pulls on the chain pulls on the rear cassette. That pulls on the spokes of the wheel, tries to turn the wheel this way. The ground does not let the wheel turn because of friction, and we have a propulsion force equal and opposite to the force of the wheel turning in this direction due to this force. We want to figure out this right here. Okay, so we're going to do the mechanics behind that. We have this equation right here that we work with, F equals ma. We identify the forces acting on the bike rider system. And I'll just write that out just so we have it. So we did this before. F propulsion is the force causing the bike to move forward, plus all the negative forces, rolling resistance, slope. Remember, we're talking biking uphill for the most part right now, and drag. And again, we're talking about a headwind versus a tailwind. Those resistance forces all add up to mass of the bike rider system times the acceleration of the center mass of the bike rider system. So just remember, mass equals bike plus rider, even though I haven't drawn the rider here. And remember, these are all our resistance forces that we need to overcome. So this propulsion force, propulsion, is added to all these resistance forces, and we get mass times acceleration. We talked about trying to reduce these, but right now I want to focus in on understanding the mechanics of propulsion. Okay, so that's the setup, and I've only drawn that force on there. I'm not drawing the other ones just because we have it in another presentation. Okay, so now what I'm going to do is I'm going to draw just the drivetrain. I've already sketched out some of it. This is the drivetrain, which consists of the pedal, the crank, the big chain ring, the small chain ring, the rear cassette, and then ultimately the wheel and the chain as well. Okay, so you should know all these parameters from the bike anatomy video. And then this is the ground right here. And I'm not drawing the rest of the bike. Okay, two equations that you need to remember here is T equals FD perpendicular. That's torque, and that's equal to the product of magnitude of force in the moment arm. And the units for torque are Newton meters. And remember, there is a direction associated with the torque, and we're going to use a counterclockwise convention as positive, meaning if the torque tends to rotate the object in the counterclockwise direction, it'll be a positive torque. If it tends to rotate in the clockwise direction, it's a negative torque. Okay, so that's equation number one that we need to remember. Equation number two is sum of torques equals I alpha. Make sure you know these parameters. That's moment of inertia, which is the tendency to resist change in rotational motion. And that has an equation, sum equals mr squared. And then alpha is angular acceleration, and that has to be units of radians per second squared, okay? So same units here, Newton meters. Now, to do this problem, to set this up, to really understand this force right here, draw it again. This is our propulsion force pushing on the bike rider's system, and this is what is causing the bike rider to go forward. All right. F, propulsion. This is what we're trying to figure out. I'm going to need these two equations. So we're going to, there's a couple ways of getting there, but I'm actually going to start with a pretty general approach. And I'm going to start with pedaling at a constant angular velocity. So pedaling at constant angular velocity. So the cyclist is trying to maintain a particular cadence, 80 RPM, 90 RPM, whatever it is. He or she is trying to maintain that constant spinning of the crank and therefore constant spinning of the rear wheel. In reality, we know that that doesn't necessarily happen, but it's a place to start. So therefore, therefore angular acceleration is 0 radians per second squared. That's nice because that's going to turn this part of the equation, the sum of torques equals I alpha, into 0. Okay, so angular acceleration is 0. This is important for the way that we're going to approach this. And what I'm going to do is break this into two problems. I'm going to draw a squiggly line down here. I'm going to do part 1. And then I'm going to do part 2. And what I'm going to do in part 1 is figure out the force that is that this crank is pulling on the chain. Okay, F chain. That's going to be part 1. Okay, then part 2 will be to figure out the propulsion force, knowing what this force is. So as I push on this pedal, this is F person, we're going to tend to rotate in this direction. And as I do that, this crank will pull on the chain, and that chain is going to provide resistance to wanting to pull in this direction. We're going to figure out what that F chain is, and then in part 2, we're going to turn that force around to over here, which will be a force pulling on the rear cassette, and that is going to be the same magnitude, opposite direction, Newton's third law. The crank pulls on the chain is going to pull on the rear cassette. Okay, so we're going to do part 1, and then we're going to address part 2. All right, so for part 1, and we're going to need these two equations, sum of torques equals I alpha and T equals FT perpendicular. So part 1, what torques are acting about this axis of rotation, which is the bottom bracket? What torques are acting about this? What forces are tending to cause rotation about that axis of rotation? Let me start another piece of paper, notes. I'm going to do part 1. What torques are acting about axis rotation, which in this case we'll call it the bottom bracket? Well, to identify that, we just look at our schematic and we can identify what forces are acting some distance from the axis rotation. And we have torque due to the person, because there's a force acting some distance, and the length, if you remember from undergrad, we can figure out the moment arm by drawing out a line of application of the force, and then drawing the shortest distance using the axis of rotation at anywhere on that line of application. Right now, I'm only going to concern myself with the perpendicular component of the force of the person pushing on this pedal. So the length of this crank will be d perpendicular person. Okay. So torque of the person is equal to force of the person times d perpendicular of the, let me write this, cross that out. I'm going to call that d perpendicular crank to stay consistent with some of our language. D perpendicular crank. That's the crank length. Typically, this could be 172.5 millimeters. That's a very common crank length. Or maybe some people like to go a little bit longer in 175 millimeters, or maybe 165, something shorter. And there's a tendency to use a more shorter crank. These are examples of crank lengths. Okay. F person is what the person is doing. This is what the cyclist is doing, pushing on the pedal. This is the torque due to the person pushing on the pedal relative to the crank length. All right, now we need to assign a direction to this. And remember, using counterclockwise is positive. So this torque due to the person will tend to rotate the crank in this direction, which is clockwise. Okay, that's clockwise. So clockwise is a negative torque. Remember, CCW is positive. That's our reference frame. Okay, so that's torque number one. The other torque is due to this force right here, pulling, the chain pulling on the big ring. The chain is providing a resistance force on that big ring. Okay, so now we have torque due to the chain, torque due to the chain, which is equal to force of the chain times d perpendicular of the chain. Where's d perpendicular? Well, I'm going to go back up here to this picture. Line of application of the force, and we'll consider this chain force acting tangentially to the big ring. So therefore, the radius of the big ring is the moment arm, d perpendicular chain. All right. So now we have d perpendicular chain times F chain. That's a torque. Calculator right here. Let's assign the direction to that torque. In this case, this torque would tend to rotate the object in this direction, which is counterclockwise. Therefore, that's going to be a positive torque. So I'll put plus sign right there. All right, those are the two torques acting on this object about this axis of rotation, the bottom bracket. Just two torques, okay? Sorry about the notes here. All right, D perpendicular crank, D perpendicular chain, F person, F chain. That's it. So those are the torques. Now, the first step is we calculate the torques. The next step is we put those torques into this equation. Sum of torques equals I alpha. Remember, the situation we are dealing with, alpha is going to be 0 radians per second squared because we're going to pedal at a constant rate. Therefore, the sum of the torques equals 0 Newton meters. We have two torques acting about this axis of rotation. I'm going to put them right here. Torque due to the chain plus, and I'm going to put the negative sign in here, plus negative torque due to the person. Those add up to 0 Newton meters. That's an N. All right, or we can say torque due to the chain, just rewriting this, equals torque due to the person. Perfect. We're getting close. Now I'm going to put in what makes up torque due to the chain. Equals F person. I don't really need to do this, but I will right now. times d perpendicular crank. That's the crank length. And now I'm going to rewrite this so that F chain is all by itself, which is exactly what we wanted to solve for in part 1. Times the crank length divided by d perpendicular chain. This is what we want. Okay. We wanted to solve for this chain force, which in our picture is this chain force right here. That's the force of the chain pulling on the big ring about the bottom bracket. That creates a torque based upon the size of the big ring. And then we have another torque due to the person pushing on the pedal and the crank times the crank length. What determines this d perpendicular of the chain? That's how big the big ring is. So we talked about this in the bike anatomy video. This would be described by the number of teeth on the big ring. This would be a 53 tooth big ring, or maybe a 39 tooth big ring, or maybe a 42 tooth big ring. The number of teeth describes how big that chain ring is. 53 tooth is going to be a bigger d perpendicular than a 39 tooth big ring. Okay, we're going to need to know that because we're going to need to interpret an equation at the end of the day. But this is the end of part 1 victory. All right, so now let's go to part 2. Let's see, I think what I'll do is I'll stop this video now and I'll start a new video for part 2. So part 1, we determined the force on the chain. Okay, thank you.